Auntie, thank you very much. I'll just sort of share my presentation. And like you have sort of introduced the topic sort of on the development in machine learning in the mineral process industries, which is well, sort of focusing on what's happening with AI in mining, as let's say to follow up on the very interesting presentation of Dr. Jassim with AI in sort of information security. Before I proceed, I just want to make sure, can you all see my presentation? I hope so.
Yes.
Is that good? Okay. I'll try to, okay, that's maybe better. Right, okay, so just to in my presentation, I'll just take a brief look at a typical mineral processing circuit and the role that artificial intelligence plays in the operation of such a circuit. These circuits, of course, used to extract metals from the earth. Essentially, we'll also take a look at the machine learning architectures that has sort of had a major impact on these operations over the last 5 to 10 years. And we look at specific examples of these applications, just a few because time is short. And I'll sort of conclude with a few summary thoughts, if you like. So just very, very briefly, if we look at the process to really extract all these metals that we are using from the earth. Essentially, we have sort of drilling and blasting in a mining operation that would generate sort of run-of-mine ore. This needs to be crushed and reduced in size. The run-of-mine ore would range from pebble size to rock size to boulders of several meters in size. And in that, in these, well, let's say large rocks or boulders, the actual valuable material is present in very, very small quantities. If you think of gold, for example, you're looking at parts per million, really. And even with many of the other commodities, a few percentage points at best. So this needs to be reduced in size, crushed, well, the different processes of crushing and grinding. And once you have that, the ore sort of crushed down to perhaps think of a fine powder size, maybe 70 to a few hundred microns in size, that still needs to be concentrated before it can be processed. And that is done by many different possible unit operations. It could be, if it's gold, for example, it could be gravity separation. Some iron ores would be amenable to magnetic separation, and so forth. Flotation is also used quite commonly. And if it's then concentrated, then that concentrate can be further processed. For example, it could be fed to a furnace where the metal could be extracted in a relatively pure form by, you know, a smelting process. And of course, the waste would also need to be dealt with. So that's the basic, a very sort of simplified overview of the way that minerals or the mining and mineral process would sort of work. Now, the role of AI or artificial intelligence in this process can be visualized as follows. Of course, all these processes, these systems are controlled. They have to be controlled, otherwise there's no operation. This is done by means of automatic control, but also by operators, especially in the mineral processing industries. Operators still play a fairly important role, unlike perhaps in, you know, some of the other, the oil and gas industry, for example. Now, if you look at sort of a unit operation, then there's sort of the measurements, the instrumentation that would measure many hundreds of variables in many cases, or it could, well, if it's a unit operation, then that could be typical. Usually these are raw measurements, so the data would need to be processed. AI plays an important role there. And then in the mining industry, predictive maintenance is also very important, especially over the last, I would say 5, 6-7 years, there's sort of been major investments in that area as well, where these data are used for the monitoring of the equipment, because you have expensive equipment in mining and so on. And of course, these data are then also used in different forms to be fed back to this controller as dynamic variables. The controller would then, well, first of all, assess the state of the plant, and based on that, if it's disturbed or it's not sort of tracking the way it should, the controller can take certain actions and sort of keep the plant on track. Of course, artificial intelligence also plays a role there. And then some of the variables are time averaged to sort of on a larger time scale to optimize plant operation, perhaps by changing the set points if the ore that has been mined, if there was some changes in that, maybe from a different part of the ore body being fed into the plant and so on. Okay, so that is sort of the big picture, if you like, in the mining industry, where the way that these systems would work in broad terms. So these artificial intelligence systems, of course, have been in use for decades, or many, well, since the early 80s and so on, of course, as well. But the changes the impacts that are sort of taking place at this point are really driven by, to a large extent, the advances that have taken place in AI. And here we are really talking deep learning methods. Now, I'm sure many of you are quite familiar with deep learning structures or architectures of these neural networks. But broadly speaking, again, there are many different types of networks. But in the mining industry, mostly, well, at least the applications that are reported in the mining and in metallurgical engineering literature, almost 90% of those applications are associated, say around 88% are associated with the use of convolutional neural networks, which is sort of one of the mainstays, if you like, in the deep learning family of networks, or one of the key members. So again, not knowing, well, many of you are probably very familiar with convolutional neural networks, but just for those that perhaps are not, very, very basically, a convolutional neural network can be seen in very simplified terms as consisting of these three parts. It will take, it's designed to process images in the first place. So it will take an image as an input, it extract features from that image, and these features will then be presented to what's referred to as a fully connected layer, which is really a multi-layer perceptron, or a conventional vanilla neural network, if you like, types of conventional networks as well. But nonetheless, this network would then use those features that are extracted from the images to predict the label that's associated with that image, because each image would also have a label that's associated with it in the training phase of the network. This label could be, is this a person, is this an object, a specific object? Classically in the internet is a cat or a dog, a piece of equipment, but it could also be a number. It could be, if there's a corrosion, if it's an image of a corroded surface, the extent of the corrosion, etc., etc. Right, so this is sort of just a very basic structure, and just to sort of perhaps elaborate a little bit more on the convolution itself, which is again in principle a very simple operation, but it's important to understand that with convolution, if you sort of look at the image on the left, the bottom side there, so the image is simply then, see that as a matrix of intensity values, of pixel values. The convolutional layer, well, there would be a filter that you would superimpose on the image. This filter has certain weights or elements, as indicated there, and it will convolve that part of the image to generate a number by summing the pairwise products of the filter weights and the image values, the intensity values, as sort of indicated there. And it will then be sort of swept across the image. It moves to the right one, and the calculation will repeat it, and it moves again, and then you get sort of a set of convolved features, a smaller set of convolved features. And this can be reduced again by another operation known as pooling, where, well, again, you have sort of a filter that's sort of on top of the convolved features. And in this case, it's simply looking at taking the maximum value of what's in its receptive field, if you like. So you have a sort of a further reduction by making use of pooling. It could also be average pooling, but let's say max pooling is quite common. And one could sort of repeat these operations so that this megapixel size image, high resolution image, can be reduced to a small set of features that can then be fed to this, let's say, fully connected layer. And in the training process, of course, so once the image is sort of passed through the network, initially all these values, the filter values in the network, these are sort of you start out with an arbitrary set of values, and during the training process, initially it would there would be a huge mismatch between the net's prediction and what it should be. That error is then fed back through the network, and the parameters can be adjusted. And gradually, as many of these images, thousands or millions, or it depends on the size of your training database, those images are fed through the network. And gradually it sort of trained, it would adapt these weights so that it can predict those labels that are associated with the images in the training database very well, but it can also generalize to other data that are statistically similar to the training data. So that's the basic process. You can say, well, yeah, so you know, is that really significant? Well, let's look at specific examples. So in this particular case, we're looking at one of those processes that I've mentioned in the concentration section of the plant, where we're using flotation. We have this fine powder, it's been reduced, but the particles are still present there in very dilute quantities. We want to concentrate them. We add that to an agitated vessel with water. So this pulp is in this tank, and it's being agitated. We also add flotation chemicals. So on top of this plant, there would be a froth that would form. And as we sort of pump air through the system, the valuable material that is hydrophobic and made more so or made so by flotation chemicals, selectively so, would all collect in the froth, where it's easy to collect. We can just skim the froth, and we get rid of well, we can concentrate we have a concentrate essentially that we are collecting in the froth. So a very versatile process, very important separation process in mineral processing across all sorts of commodities, precious metals, base metals, copper, you name it, and a very versatile process. This process is controlled by operators that often look at the appearance of this froth. You see some examples there at the top, to decide whether this process, the system is running well, whether it's, you know, there should be changes. And as you can see, so in this specific case, these are actually froth structures from a platinum plant. So the one on the left, number one, is the one is sort of what you want, because that contains a high concentration of platinum in the froth. Number two, contains somewhat less platinum, 3 even less, and 4 is basically depleted. Okay, so the operator could maybe look and see there's a difference between 1 and 4, but between 1 and 2, very difficult. And under different circumstances and you know, lighting and at night, different conditions, it is really, really difficult for the operator to distinguish or discriminate between these different froth structures. Now, with machine vision systems that have been sort of established, well, on these plants for maybe the last 30 years or so, these are designed to support the operators in their decisions. But the best decision systems, machine vision systems, until very recently, in this particular case, for example, if you look at sort of on the right-hand side, at the top there, that's sort of visualizing the features that these systems could extract from the images by traditional means, looking at things like wavelets, steerable pyramids, textons, you know, advanced engineering features, if you like. At best, these systems could maybe discriminate between these classes at around 70% accuracy. Okay, that is useful. It is valuable. You know, it can be used to support the operators, but there's still clearly plenty of scope for improvement. And that is what you get. If you look at sort of the bottom image there, that was done with a convolutional neural network. You're looking at around 99% accuracy. This is not only supporting the operator in a better way, but it's also sort of it can serve as a framework for automatic control. In other words, replacing the operator altogether, because now you have sort of a real-time system that can very accurately, in a sense, not just classify the Froth structures, because this is an so-called ordinal classification problem. In other words, high platinum, lower, lowest, sort of. So it can be used to estimate the platinum in the Froth, and on that basis, you look at sort of advanced control. So major sort of impact that this has had in this particular instance. I want to stress that this is the same technology that's used in other disciplines, like in medicine, for example, with the last few years, there's been quite a strong focus on COVID, analysis of chest x-rays, for example, to discriminate between patients that would have COVID, pneumonia, respiratory syncytial viral infections or not. Same technology in essence. It's looking at an image and classifying that image, the label in the image, if you like. However, these networks, of course, can also be used to analyze objects in an image. And this is, again, also very important in the mining industry, where if you look at, you're dealing with particles, particulate systems, and as it's sort of fed into the operating system, if you don't measure it right before it's fed into the system, well, you don't have a measurement, essentially. And you're sort of, in many ways, operating blindly. So there's been a lot of effort in measuring particle sizes as it's sort of on conveyor belts or in feed systems in mineral processing. Now, what you see here, if you look at that image in the middle, for example, this is again looking at these particles that are sort of on a conveyor belt. They've been captured videographically. The rendering in blue, that blue box is really what this convolutional neural network is seeing. And I think you'll agree that it's doing a fairly good job of seeing what is on that belt, especially if you compare that with what the traditional approach would get you. Essentially the traditional approach is not very useful. So, and the way that this works is you can say a convolutional neural network. Well, in this case, in very simplified terms, it's looking at classifying not the image, but the pixels in that image. So the pixels are also labeled, and in this particular case, the training database consisted of exactly 10 images that were labeled. But of course, there are many examples because it's looking at the pixels in the images. So it's not just 10 examples as such. But nonetheless, so through that convolutional process that I've sort of briefly explained previously, it's again extracting features. It has sort of an encoder leg there, the red side on the left. And it's sort of encoding that image again with those features, but instead of then using those to classify it, it's then using those features to then reconstruct that image, as you can see there, sort of gradually upsampling, and it has those important fusion sort of connections there to do that. But I think you sort of get the idea. So these systems are very good at, well, identifying objects of any kind in the image. Again, it's the same technology, essentially that's sort of used, for example, in autonomous vehicles, sort of recognizing other cars on the road or pedestrians, or in medicine, a classic case is sort of where one could see that this could sort of work well, and it actually does. If you look at sort of mapping the blood vessels in the eye, the retina, which is sort of important when you're looking at diagnosis of diseases like diabetes or hypertension, then classical methods struggle to sort of identify those capillary, well, micro-sized capillaries there. But because you are with the convolutional neural network system, you're looking at let's say, pixel-wise classification. Well, it can actually deal with those capillaries quite well. So again, some of the, it's a generic technology that's used very broadly. You're looking at that sort of micro cracking of materials as well. Again, going back to the mining industry, very important to monitor that and so on. And it's not only images, it's any type of signal, really. An image, a signal, hyperspectra, it's all sort of, these convolutional neural networks are really good at dealing with these signals. In this system, for example, if you look at the two signals there, can you see a change? Has a change taken place? We can't see it really. In actual fact, of course, well, one approach would be, there are others as well. Again, use a moving window. You can convert the image to the signal to an image. You can extract features. You can map them. You can see the change. This is the traditional approach. With a deep learning approach, you have the ability to see incipient changes much earlier or significantly earlier than you would with say conventional approaches, because again they are better at detecting sort of subtle changes in these images or in the signals themselves in general, sort of than say the traditional approaches. Again, very important, because now you can take action at an early stage before there's a problem, before it becomes obvious. This is sort of a classical application in predictive maintenance on the mining industry, where vibrational signals would be very important if you're monitoring, say, a pumping system or some equipment, or well, a lot of the equipment. Vibration is a clear indication of things happening with machinery in general. So and just maybe as another example, I want to stress that you don't necessarily need to use a two-dimensional input. You can also get a one-dimensional convolutional neural network that can directly deal with a signal. So this is an example where you're looking at the monitoring of the health of mining operators, but the operators sort of driving, in this particular case, earth-moving equipment. So it's monitoring the stress of the operator from his, let's say, echocardiograms that are it's sort of monitored, but it's looking at the heart rate variability, really, because that is really, again, a very important source, a very information-rich sort of signal that's has a lot of predictive potential in terms of not just stress, but other health conditions and so on that's sort of being exploited by these systems. So instead of, say, looking at the standard deviation perhaps of these and using that as an input, you simply look at the signal with end-to-end learning to get better results. Right, and then just maybe as time is sort of the essence here, very important though, although these systems are highly reliable, very predictive, there are certain cases, mission-critical cases, where regardless of its accuracy, reliability, if it cannot explain itself, if it cannot be assessed, if it cannot be validated, then it's not useful, can't be used. And this is also in the mineral processing industries, of course. These systems are also used for that purpose. So you have a predictive system that would predict, and it can sort of explain itself. But there are also instances, or a growing number of instances where these models are built, and even if they're not that accurate, it's a resource that the engineer or the operator can use to better understand the data, the plant data themselves, because you can sort of interrogate the model. This is just sort of a final example, perhaps, of monitoring of the underflow of a cyclone that's used in that grinding process. Very important, very intensive, very costly process, the grinding part of it. So the cyclones are sort of part of those circuits. The underflow of the cyclone, it's a slurry. The particle sizes in the slurry is important. That's never been, it's not measured in general. These systems can look at that underflow, of course, with some calibrated examples. They have to be trained, of course, first, but you know, that can be done. And they can also then look, so you can also look at that and say, well, so on what basis are you sort of concluding that the slurry has sort of fine particles, or it's coarse? And you can see there on what parts of the image it's focusing, and it's very similar to what the expert would also look at. So the expert would look at the angle, the flow angle, maybe some of the coarse particles that from time to time could individually be visible in the image, and with fine particles, it would look at essentially the texture, the flow structure. The expert can say, well, it's fine and it's coarse, but it cannot quantify it like the convolutional neural network can. But nonetheless, it sort of creates confidence in the model itself, if you like. Okay, so I think just to sort of, I'm very conscious of the time. So just some final thoughts, or if you like. So unlike other disciplines, perhaps, the application of artificial intelligence and machine learning in particular, although there's a long history in the mining industry, it is not well established, or there are different areas in this processing chain where it's not well established, and the reason for that is really the difficulty of you know, getting good data. That's part of it. Nonetheless, over the last few years, 5, 6, 7 years, certainly the last decade or so, there's been strong growth, especially in sensor data, the ability to interpret unstructured data in sensor systems and process monitoring. That has been really significant, and that continues to be quite significant. And it's driven by, certainly one could say, relatively established applications, but also in further developments in the technology, the deep learning technology itself. And unlike, as a final comment, sort of in the past, where, you know, in academia, there would be a development, and maybe 10 years later in industry, it would catch up. Actually, in industry and academia, you know, it's sort of, the time lag is very small as well. So something's developed in academia, and industry sort of catches up, or even, you know, industry in some cases would sort of do development that's ahead of, you know, what's happening in academia. Okay, with that, I think I'm not sure if it's possible. There could be you know, time for a question or two, but otherwise, thank you very much for your attention, and yes, I'll be happy to take questions if there's time. So how do I stop? Let me just stop my screen here. So back to you, Avanti. Okay, I see one question here. What's the present percentage accuracy of judgments by AI systems in real-world applications, example mining? That varies very, it's very application dependent, but it could be anywhere from 70 to 80% to virtually 100%. I think that the key is really sort of, if you look at sort of the advanced, and that is sort of what is useful as well. If you're looking at, say, 40 or 50%, well, that's not particularly useful. But yes, it varies a lot, but it can be very accurate. But one should remember that mining systems are, you know, there's a lot of noise in the data, so it's limited in many ways. The challenges in using machine learning applications in mineral processing, there are several challenges. Of course, previous speakers have alluded to the computational burden. Depending on the system, you need some high performance infrastructure to do the computation. So that is, and to some extent, access to that is a barrier. It's not a major barrier, but nonetheless it is. And the other major challenge is really data. One would say, well, we are sort of it's area of big data, and we are there's a lot of data about, but in mining systems, yes, as well. But access to those data and having systems that are interoperable, that can talk to each other, that is still a major issue in mining as well. So data is certainly also one of the challenges. And the third one would be people that can do the work. There are in the mining industry, there's a shortage of these skills, really.